Well, I have been around for a long time, and I've been thinking about what's going on in hardware and AR in general. And I want to convince you today that a major change is coming, a tipping point. And I'm really excited about this change, because I've been working on this for a long time. If you think about where we are now, there really is no one big killer application. So when people sit around the brainstorming session to create a hardware product for AR, you run into the following problem. You make a Venn diagram, or you try to create, a list of all of the desirable traits for your new product, and it's everything. And the Venn diagram really never has any one spot. So you're always giving up things. So for example, this is a display we made about 15 years ago. We wanted to have something very light, very beautiful, mounted in eyeglasses, but you give up a tremendous amount. Field of view is too small. You can't use it outside. You got to have prescriptive correction. If you go big, like HoloLens or some of the other headsets, you lose something that looks good. I mean, and the performance still isn't really there. So I don't think we're getting there on this path after 28 years of really working on this kind of an AR system. We don't have compelling use cases. We try to make platforms that can do everything. That's certainly what we tried to do in Google Glass. These things are over-designed, yet they're not optimized for any one thing. And we use what I call old paradigms, ways of thinking about this. I think there is a killer app coming, and at the end of the talk, I'll tell you what I think it is. But let's think differently for a minute about how these things work. If you look at how engineers think about how displays have to be designed, they have to be beautiful everywhere, because in the projector paradigm, we don't know where you're going to look. You could be interested in this mountain, or you could be interested in that rooftop. Same with monitors, camera lenses. Everybody thinks the image has to be beautiful everywhere. But how do we really see these images? Well, when you have a head-mounted display, your eye only turns over about plus or minus 20 degrees. So there's a cone where the image has to be good. And if we want to look over here, we turn our head, not our eyes. So that leads to a big simplification. Now, I'm going to try to do a demonstration on this little screen. It's likely to fail, but what I want to show you is if you follow the instructions that are going to appear right here, you'll see the demo. So just keep your eyes focused right there for now. And then now I don't know if you noticed that. Maybe you did. It depends on where you're sitting and how far away you are. But as I was rolling through that, I was changing the focus out here to try to convince some of you, at least if you're sitting in the right seat, that the resolution out here doesn't matter if you're looking here. So that means that you have a big simplification in the lenses. So if I take that into account in making my head-mounted display, I need a lens that's really good in the center, but then it can get to be not so good out at the edges. Now, if you think about how big the field has to be, and it's important to think about this for the points I'm going to make in a minute. Right now, 100-degree field of view is kind of the gold standard for what we need for functional AR and VR hardware. Ultimately, we probably need 160. You hear about 200 and things like that, but really seeing things way out here is really not very useful. 160 is probably where we need to get. But for now, 100 is really excellent. If we relax the requirements on the system in the periphery, we can get to 100 pretty easily. So what can we do with the displays we can buy today? You look at how the retina works. You have foveal resolution, or your 20/20 vision. It's just in the fovea, and you need about 1 minute of, that's 1 minute of arc resolution, so you need 1 pixel for each minute of arc. So that means that if you take a display, and I'm showing here the Kopin 2K by 2K display, that means you could build a display with 100 by 100 degree field of view with 20/60 acuity. So I tend to think of these systems now, not in terms of minutes per pixel and all of that, but what would be my visual acuity looking at the world through it? So if I made it 66 by 66 field, I could do 20/40. And 2040 is an important benchmark because that's when you become legal to drive a car. So 2040 is pretty acceptable vision. If you want 2020, you could do it with 33 by 33. My principal point here is that we're getting to displays and optics that are going to give us 2020 vision through these systems. There's even higher resolution coming. This is a display. I'm sorry I don't have a picture of it because I couldn't get rights to it in time. A display that was made by my team when I was at Google that's 18 megapixels per display, and it's this will give you 20/30 acuity with 100-degree field of view, with actually over 100 field of view. And you can drive a car with that display. And here's the reference if you want to look that paper up, Carlin Vieri's paper. So the point is, these high resolutions are right around the corner. And what could we do with them? Well, here's a 2K by 2K display, a 3K by 3K display, and that 5K by 4K display that I just described. Anything in green here is legal to drive a car. So with this display, you could make up to 140-degree field of view, and you'd still have 20/34 vision. Isn't that amazing? I mean, can you imagine systems like that? It's exciting. If you had a 3K by 3K, you could have a 100-degree field of view and still be legal to drive a car. That's pretty good. I mean, most of the apps that we're talking about in AR are limited to the things you can do with a low-resolution display. So how do we handle so many pixels? Because that's a lot of pixels. Well, remember that the fovea is only about 2 degrees across. So in terms of pixels, that's 120 by 120 that serve the fovea. So you could calculate data rates for just serving the fovea. They're pretty low. And you have to remember also that the optic nerve is only about a 10 megabit per second channel. So really, the displays shouldn't have to be fed at more than 10 megabits per second. And those are low data rates, by the way, by today's standards. So in Vieri's paper, he talked about one of the innovations we came up with on this big display, which is that we fill the whole display with low resolution data, and then we pipe in the foveal part on a separate channel and give you a foveal insert. So this is, I think, the first foveated display, truly foveated display. If you have foveal rendering, it goes perfectly with a foveated display. But you need eye tracking because you need to know where the fovea, what the fovea is looking at. What part of the image is landing on the fovea. If you know that, you can put a high resolution image there and blurry resolution everywhere else, and it doesn't matter. So there are other simplifications. For example, if you look at how rods and cones are distributed, you find out that the cones, which give you color vision, are limited to a very small range, around the fovea. And out here at 20 degrees, you probably don't realize this, right? I didn't until I read about this. You don't have color vision. You think you do, because your brain fills in the colors with what they should be. So you think you're seeing color out here, but if I were to put a color up in your peripheral vision, you couldn't tell me accurately what it is, because there are no cones in that part of the retina. So there are simplifications like that, like reducing the number of color pixels out at the periphery. And there are other simplifications you can make, like there aren't as many blue cones as red and green cones. So like, I guess that's really the purpose of pentile color filters. Your retina doesn't need it, so why provide it in the first place? So I think there's a tipping point coming, because these displays are coming, and this notion of designing for the eye is coming. Look at what's coming pretty soon. The rendering tools, like Unity and other kind of tools that are built for VR, can be adapted easily for AR. There's all kinds of image processing and enhancement that's being developed for cell phones, mostly for still pictures, but it's applicable to video. CPU, GPU, systems on a chip are coming along. Qualcomm and other companies are building these systems that can do foveal rendering. Displays and cameras reaching human acuity. The foveated displays are on the way. Eye tracking is coming along. What this means is an end to displays limiting visual performance. This is what we've always suffered with for 28 years. The displays were never good enough. That's coming to an end. And when you have that, you can solve some interesting problems, like the problem of see-through optics. pretty much everybody's talking about see-through optics. I worked on it myself with glass, and everything I did before that was all see-through. And I can tell you, this is a hard problem because if you use a wave image guide, like I think HoloLens is doing, they're very inefficient. It needs a lot of power to put an image through that, and it has a limited field of view. And when you're looking through the combiner, your acuity of the real world is somewhat diminished. So in this kind of see-through thing, your augmentation comes through the system on a chip, right? And your vision comes through the combiner, but it's diminished. And these systems are bulky. I mean, look at them. I can't show you pictures because I don't have rights to the pictures of all of the various big head-mounted displays. They're bulky. This is a huge problem. We heard it referred to earlier in one of the earlier talks. You can't portray black. I can't put a black image in front of the environment. I get only what can be added together. So if the environment is bright and my image is black, you're not going to see my image. And you get a lot of brightness competition, of course, from outside. A lot of power, a lot of heat, a lot of problems. But if you have displays that give you human vision resolution, now you can come in through the camera. Everything can come in through the camera. Send it through the system on a chip, send in the augmented data, display it on the display, and you have natural vision through the system. And I know this can be done. The latency is minimal. If you're running at 60 hertz, you won't notice the latency. You get to 20/20 vision this way. You can mediate reality through the GPU because all the information is going through the GPU. Now I can show you black because I can subtract out things I don't want. This can be much smaller and lighter than optical combining. And since you're using the GPU in your system on a chip to mediate, you can enhance people's vision. You can use all these algorithms that have been invented for photography to handle video that you're looking at. So think about, and I'm coming to what I think the killer application is. I'm just about out of time, but think about an AR device as a vision improving device. We can give you multispectral imaging, vision through smoke, image enhancement, zoom, there's a long list of things that can be done to give you better than human vision. You can also do, of course, corrective solutions, low vision solutions, lots of niche vision markets that lead to very big vision markets. This really could be the killer application. And by the way, it's an excellent platform for conventional AR. So, my last point, improving vision itself is a compelling AR use case. And we're going to be able to do it in the next few years. And that's the tipping point. Thanks.